What is stress memory in materials? Imagine a material that can remember how it was deformed and respond accordingly. That is what stress memory in materials is all about. It might sound like science fiction, but it is a real phenomenon that plays a big role in how materials behave under stress. When you apply force to a material, it experiences internal forces called stress. Some materials bounce back after being deformed, returning to their original shape, while others stay deformed. Stress memory takes this a step further. It means that certain materials can keep a record of the stresses they have experienced and use that information later. Think of it like a person who remembers how they felt after lifting a heavy box. The memory of that effort influences how they move or lift again. In materials, this memory is stored in their molecular or microstructural makeup. For example, shape memory materials like shape memory polymers and shape memory alloys can be deformed into a new shape and then return to their original shape when triggered by heat or other stimuli. This is because their internal structure encodes the original shape and stress state. Shape memory polymers have special points called net points that define their permanent shape. When heated above a certain temperature, the polymer chains become flexible, allowing the material to be deformed into a temporary shape. Cooling it down locks in this temporary shape and the internal stress. When reheated, the material remembers its original shape and recovers it, effectively recalling the stress and deformation it experienced. Shape memory alloys work on a similar principle but relying on phase changes between different crystal structures called martensite and austenite. When deformed in the martensitic phase, they can be reshaped and then return to their original from when heated to the austenitic phase. Some of these alloys can even be trained to remember to different shapes, one at low temperature and one at high temperature. This training involves cyclic heating and cooling, which introduces internal stresses and defects that help the material remember multiple stress states. Stress memory is not just about shape recovery. It also allows control over internal stresses within the material. For example, advanced polymers can be programmed to encode specific stress distributions, which can be visualized and manipulated. This ability opens up new possibilities for designing materials that can self-adjust or resist failure by managing internal stress levels. Understanding stress memory is vital for preventing product failure and mechanical breakdowns. Residual stresses that remains after deformation can influence how cracks form and grow, affecting the lifespan of a product. Materials with stress memory can either help reduce harmful stresses or, if not managed properly, make failure more likely. For instance, polymers that relax stress slowly at low temperatures may retain residual stresses longer, increasing the risk of delayed failure. Conversely, designing materials with controlled stress states can help prevent stress concentrations that cause cracks. In essence, stress memory in materials is about their ability to hold onto past mechanical stresses and respond based on that history. It is a key property in shape memory materials and has important implications for durability, safety, and performance in many applications. Knowing how materials remember stress helps engineers develop smarter, more reliable products that can withstand the demands of real-world use.